Hi everybody. Hope you're all having a good day today so far. Today we're going to be talking about equivalence relations and partitions. Now, we'll start off by just reminding ourselves of what we mean by an equivalence relation, the formal definition of an equivalence relation. Then we'll introduce the idea of a quotient set, and then we will introduce the idea of a partition and the important relationship between partitions on the one hand and equivalence relations on the other hand, and that's a relationship that's going to be important for a number of things we do later on. And then we will introduce the idea of refining a partition and the refinement of a partition. And then in subsequent lectures, in the next lecture, we will talk about the modeling of preferences and utility functions and the relationship between the two, and that'll use the ideas we're developing here. And then in a subsequent lecture, we will use the ideas that we're developing here today to talk about modeling information in economics and game theory. So that's where we're going, and so let's get started. So let's start off by just reminding ourselves of the formal definition of an equivalence relation. That is a binary relation on a set, say X, that is reflexive, symmetric, and transitive. And in the two preceding lectures, we saw a number of examples of equivalence relations. And one additional thing I think we should remember here is that we have a notion of the equivalence class of an element in capital X, and the equivalence class of an element is the set of all, let's say X prime, in capital X, such that X prime and X are equivalent. So this is the notation that's standard for an equivalence class. And of course, the most familiar example for economics is the example of an indifference map, indifference curves, level curves of a function. So let's draw a little picture of that. This is completely familiar to economics students. So we have, let's say this is X. Then this would be the indifference curve or indifference surface more generally through or containing the bundle of the point X is the indifference class because it's the set of all points in X. So here we have as capital X R2 plus. And so this is all the points in R2 plus for which the consumer, let's say, is indifferent between those points in X. Let's take another point over here. Let's call that X tilde. Well, of course, the indifference class of X tilde is the same as the indifference class of X, so it would probably be useful to point that out. And then if we have some other point, call it X bar, this would of course be the equivalence class associated with the point X bar, and so on. So one thing that you kind of notice, I think, right away here is that the indifference curves, the equivalence classes, divide the underlying set X, in this case R2 plus, they divide that underlying set into distinct equivalence classes. They divide it up, or partition it, we could say, into distinct subsets of X. And so that concept is central to what we're going to do today. And so let's give a name. I'll call it script P to the set of all equivalence classes for all the points or elements in the underlying set X. So in our example of an indifference map, of indifference curves, P would be the set consisting of the indifference curves, the level curves of, say, a utility function. So there's a couple of things to notice here. One thing that I want to really emphasize, because this is always a source of confusion for people, some people learning about partitions and equivalence classes and so on. Notice that the elements of script P, the elements of this set are subsets of capital X. So they're both elements and sets at the same time, and that poses some confusion for students often in learning about these concepts, using them. So again, the elements of this set are the equivalence classes, and those equivalence classes themselves are subsets of capital X of the underlying set. And moreover, we could say they're all non-empty. They're all non-empty subsets of capital X, and I emphasize that because, of course, the empty set is a subset of capital X, but that's one subset of capital X that can't be included here by its definition. That's just not going to happen. So this is really an important point that you have to kind of keep in mind, and sometimes you have to really come back and think about this to make clear what's going on. Well, this set of the equivalence classes, I said that it kind of divides up the underlying set or the underlying space X. It divides it up into things. So we actually refer to this set as the quotient set. So let me give a notation to that we start with the underlying set and we divide it up by the equivalence relation into these subsets, which are the equivalence classes, and we actually use this notation sometimes. It's a standard notation, but I would say while it's a standard notation, we do use it. You'll notice that I've used a different notation for this set, but this would be the standard notation for this set. I've used this notation instead because this is a little awkward to write. It doesn't, and to read. It doesn't really look like a set, and it's got the X, the slash, and the tilde. And then another reason I used P as the name of this set is that we're going to see in a few moments, we're going to be using the term partition for this set. But let's just point out here then that this is a name for the set, the quotient or the quotient set of the underlying set by the equivalence relation, and this is, as I say, a standard notation. So let's now note, in addition to this important fact that I've put in pink, let's notice a couple of other features or properties of our set P here. One is that if we have any two elements of P, any two subsets of capital X that are elements of P, then if they really are two sets, that is, they're not the same set, they're distinct, they have to actually be really distinct. That is, they have to be disjoint. They can't have any elements in common. And of course you can see that in the indifference curve example. We can't have any intersection between two indifference curves. Then we would have a particular bundle that would be on more than one indifference curve, and that kind of would mean that it's really all one big indifference curve. Again, it would just be one single set. So that's one property, and we often refer to that informally by saying that the elements of P, the subsets of X that are in P as elements, are mutually exclusive. Again, they're mutually exclusive because they can't have any point or points in common, any two of them. And second property is that if we take the union over all of the elements of P, now of course you say union of elements, but of course remember the elements of P are subsets of X. So we take the union of the sets in X that are elements of P, that is equal to the entire underlying set. Now we could say that another way. We could say that for every element of capital X, there exists, let's say, a set in P such that X is in the set S. So that when we take together all of the elements of P, all of the subsets of X that are in P, one of those set, put it a different way, every element of the underlying set has to be in one of those elements of P. So these features, these properties of a collection of subsets of an underlying set, whenever we have a collection of subsets of an underlying set, and that collection of subsets, call it P, they're non-empty, and they satisfy these two conditions, they have these two properties, that is something that occurs in mathematics and in economics, but I'd say especially in mathematics, over and over and over. This is a fundamental feature of mathematics, the notion of an equivalence relation and associated set, like the set P here, that has these properties. That reminds me, you'll actually notice that I've said about a few concepts that you see them over and over in mathematics or in economics. And whenever I say this over and over, it always reminds me of a song from years and years ago by Lloyd Price, Over and Over. Great song. In fact, I start each one of these lectures by saying, I hope you're all having a good day today so far. Well, if you are or you're not having a good day, you watch this video of Lloyd Price performing the song over and over. I guarantee you will. It'll make you smile and it'll make your day. I'll actually provide a link to Lloyd Price singing over and over down below in the description of the video. Okay, with that aside, off to the side, let's return to the subject at hand here. And I've said that we see this over and over, and so of course you're going to say, hey, we probably then elevate this to a definition. And of course that's exactly what we do. We elevate that to the general concept of a partition of some underlying set. And so a partition is just a collection of non-empty subsets of the underlying set, like this one, and it's a collection of non-empty subsets that satisfies these two conditions. So whenever we have that, we have something called a partition. So what that means is that for our indifference relation here, that indifference relation defined indifference classes, which were non-empty subsets of the underlying set, and they defined those equivalence classes in such a way that if we took the set of all the equivalence classes, it would do these things. They'd be non-empty, would satisfy 1, satisfy 2, so therefore that's a partition, and that means that for any equivalence relation, we can do exactly the same thing. Everything we did here did not depend on this equivalence relation being indifference among bundles or alternatives for an individual to choose from. These conditions, these properties that define a partition are always going to be satisfied if we're looking at the set of all the equivalence classes that are defined by some equivalence relation. And that is what this next theorem says. The theorem says if we have an equivalence relation on an underlying set X, then the quotient set, like this, that is the set of all the equivalence classes, is going to be a partition. Oh, I just noticed that I left something out here that I meant to write, so let's write that in here now. We say that the first condition here for a partition is that the partition consists of sets that are mutually exclusive, and the second condition, we often describe that by saying that the partition consists of sets that are exhaustive in that they cover all of the underlying set X. They exhaust all the elements in X. So we often just describe a partition as a collection of non-empty subsets of the underlying set that are mutually exclusive and exhaustive. Mutually exclusive and exhaustive, a collection of sets. And that's supposed to be an S there, not exhaustive, exhaustive. All right. And so you'll notice in the theorem that there's a little a over there. And so you might guess that the theorem actually has two parts, an A part and a B part. And if you guess that, you would be correct. But I'm not going to do the B part quite yet. Before doing that, I want to go through several examples of partitions where we can just use part A to talk about these candidates or potential partitions. So let's do just 2 or 3 simple examples. Let's first take a set that consists of only one element. That element is the whole underlying set capital X. So that's a capital X. And so we've got a set with one element, and the element is the set capital X. Is that a partition of the set capital X? Well, yes, it is, because it consists of elements, only one, that are subsets and a non-empty subset of capital X. And the part in brackets here, of course, is actually vacuously satisfied because there is only one element here. There's only one subset that's included, so we can never have two distinct subsets. So this implication is vacuously satisfied, always true. So that means this implication here is always true. So mutually exclusive, a single mutually exclusive set. And of course it's exhaustive because every element of X is included in capital X. And so capital X plays the role of the capital S over here. So indeed, That's an elementary, simple partition of capital X. And so what about the set consisting of, or whose elements, the set whose elements are themselves singleton subsets of capital X? And it's all the singleton subsets because all the x's are over here on the right-hand side of the vertical line. So this is a set of subsets of capital X because the bracket's here. Each one's a non-empty subset because each one has an element x in it, a single element in it. So they're non-empty subsets. Clearly they're mutually exclusive because any two distinct sets, they're two distinct elements of X, so their intersection is going to be empty. And the sets are exhaustive because every element of X is included. So this is a set of elements which are non-empty subsets of X, and they are mutually exclusive and exhaustive subsets of capital X. One last example before I want to go into a little more extensive example. And this example is one where, let's say we start off with a subset of capital X named S, and we take as our candidate for a partition the set consisting of capital S and capital S complement. The set capital S, subset of X, and its complement, and I have to specify here that S is neither the empty set nor the whole set. Because if S were the empty set, this would be an empty set, so we wouldn't have non-empty subsets. And if S were the whole set, then its complement would be the empty set. And so again, I wouldn't have both of them being non-empty. But so long as S is not the empty set, not the whole set, then this set with two elements, each of which is a non-empty subset of capital X, is a partition because they're mutually exclusive. No element is in a set and its complement. And they're exhaustive because every element is in either a set, the set S, or its complement. So this is another partition. And of course, any non-empty, not the whole set, subset of capital X would work here as a partition. In fact, that's a common partition that we often see. These are sort of elementary partitions. We see them, but they don't do much, right? But this is common. We see this a lot. So three simple examples. And what I want to do now is I want to do a little more extensive example, and to do that I'm going to take off everything over here on the right in order to get some more space to do that example. So we'll be right back as soon as we take everything off here.